Alright, so we're going to start by finishing up chapter 3, which the last section in it is solving systems by graphing. We'll do a couple with algebra, but the nice thing about graphing is if you get a system you can't solve with algebra because it doesn't factor, like you can't use the rational root theorem, you can't use synthetic division, whatever the case is, there's always a way to solve it with the graphing calculator. Okay, so remember that a system is when you have two or more equations and two or more variables. I think most of the systems that we look at today are just going to be two equations and two variables, but they could go as high as you want. You can have as many equations and as many variables as you want. The most common problem is when the number of equations matches the number of variables. So, two equations, two variables, three equations, three variables. You can have what's called an overdetermined or underdetermined system, which is when you have more of one than the other. Okay, we're not going to look at that too much. It can happen. So if you're solving a system that has two variables, the solution is an ordered pair. Okay, it's a location. So make sure that you write both numbers, the x value and the y value. So graphically, I don't really think there's much new. You should already know this, but to solve a system graphically, you're just going to look at where the graphs cross. And now that we know a little bit about polynomials and what they look like, you should try to keep in mind how many times things could cross. Like if you had two lines, assuming they're not the same line, how many times can two lines cross at most? Right? Just once. Just once. How about like a parabola in a line? How many times could they cross at most? Chris? Yeah, you could get twice. So just kind of keeping those things in mind, because if you had a window like this, let's say the dotted part is off the screen, and you had a line in there, well, just keep in mind that you might have an intersection point off the screen. But if you know it's an x squared, you know it's a parabola, you should check for that. Okay. Questions on that? All right, so let's take a look at an example. All right. If you were to graph both of these, you'd have to get y by itself. Okay, but before I even do that, does anybody recognize what kinds of shapes those equations will be? Jared? Do you recognize what shape they would be?
No.
All right. Do we have any exponents on the variables?
No.
No, so there's no exponents. Do we have any fractions with variables in the bottom?
No.
No. So these are going to be pretty straightforward then. The exponents are only to the first power. There's no variables in the bottom. So what's one of the most basic graphs we can have?
A line.
A line. These are two lines. All right. But to graph them, we got to get them in y equals mx plus b. So Tori, if I wanted to get that in y equals mx plus b, the first one, what would be the two things I would have to do?
Subtract 2x from both sides of the equation and divide by 3.
Yep, so I'm going to subtract the 2x and then divide by 3. Now, the reason I wrote it as negative 2x plus 5 is because I'm trying to get it in y equals mx plus b. It's not necessary, but that's kind of the standard. So I minus the 2x, and then I'm going to divide by 3. Okay, so that gives me a slope of negative 2/3 and a y-intercept of 5/3. All right, let's do the same thing here. Again, we got to get y by itself because that's the only way you can type it in on the calculator. Maybe other calculators you can type it in this form, but our calculators can't. All right, so what would be my two steps to get y by itself in the bottom one? Yeah?
You would add 3 and then divide by 5.
You would add, can you just say it one more time?
3x.
Yep, I'm going to add the 3x. So it's going to become positive 3x and then divide by 5.
But if you're adding it, wouldn't it just disappear? Because if you're adding 3x to a negative 3x, wouldn't it become 0?
On the left side, yep. So that's why it disappears from the left.
Oh, because you have to add it onto both. Okay.
You got to add it, and then on the other side, it's not there, so then we're moving it. Yep. Okay, so quickly, I can tell these lines aren't parallel. So they're going to cross somewhere, because they don't have the same slope. So let's graph them and see where they cross. All right. The easiest way to type in that fraction is probably, you can type it a couple ways. Negative 2x over 3. That's one way. As long as you keep the x in the top, it should not be in the bottom. Plus 5/3. And on the second one, I'll show you a different way to type it in. You could type in 3/5 with the x on the outside. Make sure you put a parenthesis there, because if you don't, it's going to do 3 divided by 5x. And you don't want the x in the bottom. Okay, so 3/5 x plus 21/5. Yeah, probably a good idea to put parentheses around the y-intercept too, because it's division, so let's just do that. So let's see, 21/5, that's about, what, 4? A y-intercept of a little above 4, so it should be on the screen. And that's it. So now we just have to figure out where they cross. Did anyone remember the buttons I pressed to do that? Yeah.
Second calc.
Second calc.
And 5.
And then 5. Now they only cross once, so it's not super important in terms of the guess. I also only have 2 curves on the screen. It's not like a problem where I got 3 or 4 things at the same time. So I want the blue one, I want the red one, and the guess, well, it doesn't matter.
Wait, second calc 0?
Second calc intersect.
Oh.
And there's your answer right there. Oops. So for kind of a messy equation, the answer actually came out kind of nice. So the answer is negative 2, comma 3. If you don't want to write your answer as a coordinate, you can write it exactly the way the calculator does right there. That's fine too. X equals negative 2, y equals 3. But understand it is a coordinate. Any question on that? Okay, so not super bad to really solve by hand. We could do it with algebra if we had to as well. You just have to take that and plug it in right there. You just use substitution. So it would be negative 2/3 x plus 5/3 equals 3/5 x plus 21/5. Kind of a pain with all the fractions, but you could do it. All right, so this one says find the number of solutions. Okay, let's look at the top equation. Well, actually, no, let's start with the bottom. What kind of equation is the bottom one? If you had to describe like what it's called based on the highest exponent. Yeah, Kaylee? It's a parabola because it's a quadratic type equation. So the bottom one is a parabola. The top one is a cubic. So if you remember cubic, how many turns can a cubic graph do? Yeah. It can cross the x-axis 3 times, but it can't turn 3 times. Anyone remember how many times it can turn? Yep.
Turn twice.
Twice. So if I'm picturing a cubic, all right, could look something like that. A parabola could look something like that. So I'm thinking at most it could cross each other 3 times. All right. I don't think you could get more than that. It is possible you get 2, 1, but you won't get none because the cubic is going to go down forever and it's going to go up forever. So at some point it's going to hit the parabola. Okay, so you'll get at least 1, maybe up to 3. This time they just said to find how many. You don't have to actually find them. So type it in. Negative. Let's get rid of that. negative x cubed plus 3x squared plus x minus 3. Okay, so there's my cubic and my parabola. So the reason it's kind of important to think through what it would look like is because something might happen off the screen that we need to look at. So we kind of know what we're looking for, and if we don't see it, we might have to zoom out. There's my cubic. There's my parabola. All right. Am I seeing everything that I need to be seeing here? What do you think? Do you think they... So how many times do you think those cross? Yeah? 2 times? So you got a guess for 2. Yeah? 3. Yeah, I think they're going to cross 3 because to me it looks like the blue and the red are getting closer and closer. The only way to tell is to take your y min and try let's try negative 40. Remember, we don't have to find what it is. We just have to make sure that they do cross if we're going to write that they cross 3 times. So we definitely have 2. And yeah, they do cross another time. Could I actually find it? I'm not sure that I went low enough to find it, but I can tell they're going to cross. So the answer is 3 times. SC3. Okay. Any questions on that? If you wanted to actually find the answers, then you'd have to do second calc intersect 3 times to get each one separately. Some calculators, I think, can do them all at the same time, but ours don't. As far as solving this one with algebra, if you tried to do substitution, you'd end up with a pretty tough equation to solve because this exponent of 3 is what's really going to mess you up. Okay? You can't use the quadratic formula on something that has an exponent of 3. So it could be kind of hard unless the rational root theorem worked and then synthetic division. But other than that, it would be tough to solve by hand. All right, so this is one they do want us to try with algebra, and then we'll do a graph as well. And this will be the last one for this section. So let's do it. Let's do it with algebra first. Or algebraically. Okay, how would I solve that algebraically? I kind of mentioned it on the last couple, even though we didn't do it. Now we're going to do it because it's going to work out nice. Yeah.
Substitution.
Yeah, just use substitution. Y equals 3x. So take what y equals and plug it in. So we get 3x equals x cubed minus x. Now, what I would do is, same thing we do when we solve quadratics, what number do we get it equal to? Yeah.
0.
Yeah, we're going to get it equal to 0. So I would do that. You might be saying, well, we're still going to have that cubed. I thought you said things with an exponent of 3 were hard to solve. Not if they have a common factor. Okay. In this problem, if you look at the 2x squared, the 5, the x cubed, the 3x squared, the x, and the negative 3, they all don't have a common factor. But here they do. What's the common factor between x cubed and negative 4x squared? Yeah.
X squared.
Yeah, it's x squared. Okay, so Kaya told us that common factor, but now what we're going to do is factor it out. So we've got x squared. And what would that leave me with if I factor that x squared out? Yeah?
Why is it x squared?
Why is it x? Oh, I'm sorry. Yeah, it should just be x and x. So Kaya, you were right with the incorrect problem that I wrote. But if you write it correctly, it's just minus 4x. So the common factor is x. Thank you. So now if you factor x out of x cubed, Gabe, what would be left there?
X squared minus 4.
Yep, x squared minus 4. And look what just happened. That's a difference of 2 squares. You can factor it again. How does x squared minus 4 factor? Yep.
X plus 2x minus 2.
Yep. And now we have something times something equals 0, which means there's 3 different opportunities to make this 0, setting each factor equal to 0. If we set the first factor equal to 0, how about Kathleen? What would make the first factor 0?
0.
Yeah, just 0. Second factor, how about Madison? What would make the second factor 0?
-2.
Yep. And the third factor, positive 2. So solving that algebraically, not too bad because we were able to factor out x, and then it factored again as 2 squared, so we just got lucky. All right, let's try it graphically. So we already know the answers, so a standard window from -10 to 10 on the x-axis, that's plenty to show all the intersection points. So x cubed minus x, and what was the other one? 3x. When it doesn't go back, it stays as like an exponent. X cubed minus x. Okay, so we're looking for intersection points at 0, -2, and 2. I'm zoomed out kind of far, but I think we'll still be able to see it. All right, so graphically. All right, so we have a point here, here, and here. And if you look at them, you get -2, 0, and 2. So we have all the x values, but we didn't finish the problem yet. Because remember, the answer is a coordinate. So if you're doing intersect, it'll give you the x values. And Kaya, what were you going to say?
At the top, like the top right quadrant, it goes and intersects again.
Up here?
Yeah.
Well, this is a cubic, right? So this cubic is just going to curve up, and this line is just going to keep going that way.
Okay.
Does it look different on yours?
Yeah.
Did you type in x cubed minus x and 3x?
Yeah.
Okay. And you're not just looking at this intersection point right here? So you get 4 intersection points?
Oh no, it's just shifted upwards.
Okay. Yeah, it's just because my zoom is a little lower. So yeah, we only get the 3. And if you do second calc intersect, you'll get all the x's. How do I get the y values? Now that I have the x's. Rob?
You just do the second calc.
Okay, if we were going to do it with the calculator, we could do second calc intersect. How about if I was going to do it by hand? Yeah.
Just plug it in for x.
Just plug them in for x. And you could use either one. I would use the bottom one because they're simpler. So the y values are triple the x's. So 0, -6, and 6. And those are the corresponding answers. If you want to write them as coordinates, you could do that too. But that's fine. Okay. Any questions on that? Okay, so it's solving systems graphically, a little bit algebra, but nothing, nothing too fancy. All right, so now we're going to start to take a look at chapter 4. Okay, so chapter 4, we're going to kind of get away from polynomials by themselves. Okay? We're going to look at what's called a rational function. So I said we're going to get away from looking at polynomials just as like a single polynomial by itself. But rational functions are really made up of polynomials. The difference is you have a polynomial on the top divided by a polynomial in the bottom. So an example might be like x cubed plus 2x minus 5 divided by x squared minus 3. That's a rational function. And q of x could never equal what? Because if we did this, we would divide by what I'm thinking. Right. Q of x could never equal 0. It's got to be something that's not 0. All right, so anytime you've got a variable in the bottom, we've got to check, could that equal 0? And if it could, what we're going to end up with is something we haven't really talked a lot about, but we're going to end up with an asymptote. Okay, there's different kinds of asymptotes. Some are horizontal, some are vertical, some are even slanted, some are even curved. Okay? We'll talk more about those later on. That's not an example we're going to solve. That's just an example of another rational function. X squared plus 1 divided by x minus 3. Okay, there's another one. So some of the things we're going to do is we're going to find asymptotes, we're going to find domain, find range, things like that. So like in f of x, the domain would be every number except 3. You're not allowed to plug 3 in for x, because you'd divide by 0 if you did that. Any questions on that one? Just a couple examples. All right. So the domain is pretty straightforward. Range can be a little trickier, but the domain is every number that would not make the denominator 0. You don't have to worry too much about the numerator when you're focusing on the domain. You want to look at the denominator. So what I usually do is I set the denominator equal to 0, and then I find the number that would cause the bottom to be 0. And then I say the domain is everything except that number. Or numbers. It can be more than one. So let's look at an example and see if we can find the domain. So it's x squared plus 1 divided by x minus 3. Okay, what's the domain of that one? Yeah, Nathan?
All real numbers but 3.
Yeah, it's all reals except 3. So 2 ways you could write your answer. All reals except 3. Or you could say it's every number from negative infinity up to, but not including 3. Or you can pick any number from 3 to infinity, not including 3. Okay, I'm showing you both ways because if it's a multiple choice question you get, you might see this notation rather than it written out in words. Questions on the why it's 3 or the 2 different ways I wrote the answer? Okay, that's that one. Let's try this one. So I want to find the domain. What do I have to focus on for domain again? Numerator or denominator? Denominator. So this one's a little harder to look at though, because if you look at the bottom, I need to rewrite that. Does anyone have a guess what I'm going to do with that? That's going to make it easier to figure out the zeros. Yeah, we're going to factor it. Yep. To find the zeros by hand, with a quadratic, you want to factor it. So you can leave the top the same. see if we can factor the bottom. Anybody see how that's going to factor? Yeah.
It's x minus 1, x plus 1. I mean, x plus 2.
X minus 1, x plus 2. Let's check. So we get x squared plus 2x minus x. Looks good. Yep, it's perfect. Now, we should be able to tell me the domain a little easier. What's the domain in example B? Yep, Kaya.
All reals except for 1 and -2.
Yep, so all reals except 1 and -2. Okay, so that's the trick there. You got to factor. And C, C is actually a little easier than B. It's the same kind of problem, but it's already factored. Yeah.
On the last one, how would you write it with like the infinity?
With that notation?
Yeah.
So kind of think of it as like the answer is basically this number line. Everything here, there'd be a hole there, everything there, and there'd be a hole there. So if you want to write that, it's 3 separate things you have to write. You can pick anything from -infinity up to -1, or, now do the next section, -1 to positive, wait a minute, did I switch the numbers?
Yeah.
Not a huge deal in terms of the concept I'm trying to show, but it's not actually the answer to this problem. So -infinity to -2, or the section in the middle, -2 to 1, or 1 to infinity. So 3 separate sections. All right, and let's look at the last one. This one, let's just write it in words because it's very similar to the example B. What would be the domain here? Emma?
All reals except 1, 2.
All reals except 2 and -4. Yep. And you could write it in the other notation if that makes you happy. Okay. Any questions on that? So that's domain. So the simplest rational function you can have, okay, the last 2 that we did, those were kind of fancy. It's got x squareds and all this stuff in it. This is the simplest. 1 divided by x. It's a rational function. And if you're thinking, well, how is 1 a polynomial? Because I said it has to be a polynomial in the top and a polynomial in the bottom. A constant is a polynomial, technically. So that's a polynomial. That's a polynomial. And that's called the reciprocal function. Okay, and I'm going to show you what the graph looks like. Now, what value are you not allowed to use for x here? 0. So something weird is going to happen when the graph starts to approach 0. Right, let's look at it and see. I meant to do zoom 6. I think I did zoom 7, but that's fine. That's what the graph pretty much looks like. If you do zoom 6, you'll just be zoomed out a little further. All right, so let's look at what happens as x approaches infinity, which means as you go further and further and further to the right, and negative infinity, further and further to the left. What's happening to my y value in both cases as I head further and further right or further and further left? The y value of that graph is getting what? Yeah.
Closer to 0.
Yeah, it's getting closer to 0. So as x approaches infinity and as x approaches negative infinity, the y value is approaching 0. As you approach infinity or negative infinity, if you're getting closer and closer and closer to something, in this case it's 0, I could easily make it something else. I could shift everything up 2. Now it wouldn't be 0, it would be 2. But that number that you're approaching is called an asymptote. In particular, we're going to start by looking at the horizontal asymptote. Okay, so the line y equals 0 is a horizontal asymptote. And the way we usually show it is we take the line. It's usually a line, so let's make it a line. It's going to be small, so I don't think you're going to see the arrowheads on it. We make it a dotted line. Okay, and we would put that right in there. Right. So that's how we generally show an asymptote. The dotted line, and it gets closer and closer, but it never reaches it. Okay, so the way you find a horizontal asymptote is you look at what's happening in your graph very far out. Look at what's happening as x approaches infinity or as x approaches negative infinity. Now, some people say, well, an asymptote is something you never cross. That's not true. You can cross it. Like, see this particular graph? It crosses the asymptote early on, but then as I head further and further out, now it looks like it's kind of leveling off, and it's just going to get closer and closer and closer to that dotted line, but it's never actually going to touch it. All right. Here's another one, where this time the graph actually never does cross the asymptote. But you want to be looking at what happens really, really far to the right or to the left. You can even have, I don't know, I think on page 217 they have this as an example. Something like that. So that graph is getting closer and closer to 0 as I head towards infinity, and it just keeps crossing the asymptote the whole time. Right? I drew it as an axis, but I could put it in as a dotted line, and it's just kind of oscillating around the axis. Okay? So that's also considered an asymptote. All right. So algebraically, the easiest thing to do in your mind if you don't have a sketch is just pretend x is a really big number. Pretend x is 1,000,000. Plug it in and see what you get. All right. So if x was a really huge number, what happens to that fraction? 1 divided by x. Chris?
It's really small.
Really small, right? And it's getting smaller and smaller, approaching what number?
Like positive infinity, keep going up.
Well, you said the fraction's getting small, right?
Yeah.
Infinity's pretty big.
Well, if x equals.
Oh, if x equals infinity, yeah. So x is getting bigger and bigger, and the fraction is getting smaller and smaller.
Yeah.
Approaching what number?
And like your range, like the number ends.
So I'm looking for an actual number, like 5. So there is an actual number that what's in that box is getting very, very close to as x gets huge. Yeah?
0.
0. Like I said, pretend x is 1,000,000. If you do 1 divided by 1,000,000, it's very small. It's never 0, but it gets smaller and smaller and smaller. So if you take a number that's almost 0 and add 2 to it, what do you get? Oh, Gabe? I'm sorry, Gabe? Yeah.
Almost 2.
Yeah, you get almost 2, just a little bigger than 2, right? So as x gets bigger and bigger and bigger, your horizontal asymptote is approaching, or is 2. Your curve is going to get closer and closer to 2. So it's always y equals for our horizontal asymptote, and it's y equals 2. Sorry, John. Okay, any question on that? All right, so let's look at this one. 1 divided by x minus 3. As x gets really, really big here, or really, really small, like or really big negative, positive or negative, what is this going to get closer and closer to? Like this whole thing. You know, again, pretend x is 1,000,000. If you plug it in, what do you get? Yeah. Basically negative 3. Either a little above or a little below negative 3. If you plug in 1,000,000, you get 1/1,000,000th minus 3. That's like negative 2.9999999. Well, if you let x be negative 1,000,000, negative 1/1,000,000th minus 3 is negative 3.000001. Okay, so it's your asymptote is y equals 3. Make sure you put y equals for horizontal. X equals will be when we do vertical. Okay, they didn't ask for vertical here, just horizontal. So it pretty much just ends up being the number at the end.
Why is it positive?
Negative 3, yeah.
Okay.
Thank you. Yeah. I think I said negative 2.99 and negative 3.001, but then I wrote positive 3. So it's pretty much just the number that's at the end if you want to focus on the horizontal asymptotes. All right. So if we kind of remember what 1 divided by x looked like, it looks like that. So if I draw that, and it comes down, goes like that, and same thing here.
Was it 1 over x plus?
Plus 2, yep. So this is not the graph, this is the original. What is the plus 2 going to do? Yep.
Shift everything up to.
Shift it up 2. So now this is going to go 1, 2. This is going to go 1, 2. So if you think about it as a transformation, it's not really that hard to sketch. Just take the original and do what the transformation says. So it's shifted up 2. Now your asymptote, it's a little thick for a dotted line, but that's okay, is at y equals 2. Any questions on that one? So all the transformations that you know still apply exactly the same way they have all along. And we'll be looking at them in more depth. All right, so let's look at a graph that has 2 horizontal asymptotes, different ones. So what we're going to do here, in this problem, we're going to have to break it into cases, okay, 2 cases. And I think once I show you the problem, you'll know what the 2 cases are going to be. One's going to be if x is greater than this, one's going to be if x is less than this. And in general, when we write a polynomial function, we always want it to look something like this. 1 over, and you might have something here, here, and here. So depending on what you put in front, that can change your vertical stretch. Depending on what you put in the bottom, that can change your horizontal stretch and your shifting left and right. Depending on what you put at the end, that can control your shifting up and down. This is not written like that. We should have a 1 over and then go from there. All right, so the only way to fix this is to use division. So with absolute value, what do you think the 2 cases are we're going to look at when x is greater than what? Yep. But if you were trying to explain to someone how to do absolute value, if x is this type of number, you don't have to do anything. If x is this type of number, then you have to do something. What are the two cases? Yeah?
If it's positive, you don't do anything. If it's negative, you switch the sign.
Right, you take the opposite of it. So let's look at the case where it's greater than or equal to 0. Well, if x is greater than or equal to 0 already, you could just take away the bars. The bars don't even matter, okay? Because x would already be a positive number. So let's do that out and see how we go. So it's such a short problem, whether you use long division or synthetic division, it doesn't really matter. So we'll do x plus 3 divided into x minus 2. And again, I don't care which type of division you use. So x goes into x one time, multiply it back out. 1 times x is x. 1 times 3 is 3. Wait, did I set that up right? Did I put the... I always get mixed up when I write it as long division. So if you were dividing like 5 by 8, 8 would go on the outside and then 5. No, I did that right. So we're okay. Sorry. All right. So now, let's see. What do you want to make sure you do with these columns?
Line them up.
They're lined up, and now what operation? Do we add, subtract, multiply?
Subtract
them. Okay, so we get x's cancel. -2 minus 3 is -5. I'm done. Okay, so now I could rewrite this as my quotient is 1 plus my remainder over my original denominator. Just like writing a mixed number, except our mixed number has a variable in it. So it's 1 plus -5 over x plus 3. Now, technically, since it's -5, if you wanted, you could just say 1 minus 5 over x plus 3. Same thing. All right, so let's look at this one. What would be your horizontal asymptote there? As x gets really, really big, pretend x is a million. You'd have -5 divided by 1,000,003 plus 1. That's pretty close to what number?
-5 over x.
So what would be what would be the number?
1.
1. Yep, it's very close to 1. Okay, as x gets bigger and bigger and bigger, this part basically disappears and becomes 0. So we get a horizontal asymptote of y equals 1. Now, let me put it over here. So the horizontal asymptote, y equals 1. And we get one other one. So now we have to look at the case when x is less than 0. So what did we say to do if you want to take the absolute value of a number that's less than 0? What do you do to it? About that?
You would switch the sign.
Switch the sign, right? Which means make it negative. And you think, well, wait, make it negative? Yeah, if you have a negative number and you want to take the absolute value of it, make it negative, and then it'll cancel and become positive. So this is your other case. If you had something less than 0, you would have to make the number negative that you have, and that would effectively take the absolute value of it and make it positive. All right, so the first asymptote we have applies to when x is greater than 0. This one is going to be heading in the other direction when x is less than 0. Okay, so let's set it up and see what happens. So we've got negative x plus 3 divided into x minus 2, and it's pretty much going to be the same thing, just the sign is going to be a little different. So negative x goes into x, we get negative 1, multiply it back out, we get x minus 3, and now subtract those columns.
Why is it negative x plus 3?
Negative x plus 3 because you're taking the absolute value of x. And the only way to take the absolute value if you have a number less than 0 is to change the sign of the number.
Okay.
Okay, when you subtract here, those are gone. Negative 2 minus minus 3 gives me 1. So now I get quotient plus remainder over divisor. So now that's what my equation is basically going to be when I'm less than 0. What's the horizontal asymptote for that one? Yeah? Negative 1. So your two asymptotes are at 1 and negative 1. Let's graph it and see what it looks like. So what that means is we're going to have a graph that's kind of sandwiched between two things. Or at least that's how I'm thinking it should look. Or at least it's going to look like it's getting closer and closer to two things as you go in different directions. So we've got x minus 2 divided by, absolute value is under math and number, and it's the first option. So absolute value of x plus 3. All right, let's see what we got. If I zoom out a little bit so you can see a little more, it's definitely sandwiched between negative 1 and positive 1. It's never going to go above 1, never going to go below negative 1. That's it. Any question on that? So a little tricky, but that's how you have to think about absolute value problems. You have to break them into cases in order to find the asymptotes. Because you can't do long division with an absolute value of a variable. You have to have just a variable. So that's why there's two cases. Okay, so let's go back to the basic function. Okay, just 1 over x. Now, I don't want to look at what happens as x is getting bigger and bigger and bigger. I want to look at what happens as x gets very close to 0 from the positive side. So what that means is start at like 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, coming that direction. What's a number that's very close to 0 on the positive side? 1? How about even closer? Yeah?
0.0001.
0.0001. So let's see what happens if we plug in 0.0001. I get 10,000. So what's happening, and we already kind of saw it on the graph, is this graph, as you get very close to 0, is almost going straight up. If it goes pretty much straight up, what does that mean it's approaching? Yeah. It's approaching infinity. So as x approaches 0 from the positive side, that's the notation from the positives, the y value is approaching infinity. Well, what happens as you approach 0 coming from the negative numbers? Let's look at that. So as you approach 0 coming from the negative numbers, what does it look like is happening to my y value? It's going to negative infinity. So that behavior of approaching infinity as you go on one side, negative infinity as you go to the other, indicates another type of asymptote, and that's called a vertical asymptote. So for the graph that I showed you, 1 divided by x equals 0 is a vertical asymptote. Notice anytime you write the equation of a vertical line, it's got to start out with the letter x. All right, so vertical asymptote doesn't have to just be at 0. It can be at different numbers. In my description, I'm saying, let's say it's at h. That means as you get very close to h, from either the positive or the negative side, the y value has to either go up towards infinity or down towards negative infinity.
X equals h? Is
Yep.
that what it said? Okay.
So x equals a number is a vertical asymptote if, as you approach that number from the left and the right side, you either go towards infinity or negative infinity. That's a characteristic of vertical asymptotes. Now, there's an easy way to tell where the vertical asymptotes are. And if you know how to find domain, you already know how to find the vertical asymptotes. So as long as your numerator and denominator don't have common factors, the vertical asymptotes are all the values that make the denominator 0. They're all the values that we said are not in the domain. Now I say if they don't have common factors, because does anyone remember what happens if you have a common factor in the top and the bottom? It was another way that a graph can have a discontinuity. It was a very small, we used a word to describe it. Remember, it's not a break, but it was called something else. Something you can't see on the calculator because it's so small. Yeah? A hole. If your numerator and denominator have a common factor, so let's say I asked you to graph this. And you said, oh, there's a vertical asymptote at -2. I'd say, well, -2 does make the denominator 0, but the problem is if you factor the top, it factors into one of the factors that's in the bottom, which means you will not get a vertical asymptote, you will get a hole at -2 if you sketch that. Okay, so as long as there's no common factors, asymptotes always occur where the denominator is 0. Okay, so I'm going to write my equation for a vertical asymptote. How about Jacob? Anytime we're writing the equation of a vertical line, it always starts out what letter equals?
Y.
Y is for horizontal. X. So x is vertical. And what value would make my denominator 0 in this case? Yeah. 2. X equals 2. There's your vertical asymptote. So vertical asymptote, look for the value that makes the denominator 0. Let me try this one. Okay, what would be my vertical asymptote here? Yep. -3. What's that -1 doing? That's going to affect something, but it does not affect the vertical asymptote. What does that affect? That affects the horizontal. If you shift something down 1, which is what that's doing, think about a vertical line that goes up and down forever. If you shift something down one that goes up and down forever, it has no effect at all. So that's why shifting up and down does not affect vertical asymptotes. It would affect the horizontal. And then sketching, that's kind of the same idea. So I'm going to hold off on sketching. All right, so this says describe the horizontal and vertical asymptotes, and then describe basically the transformations. So we're looking for vertical stretch, horizontal stretch, things like that. Now, that's not written the way it needs to be. This is kind of like the absolute value problem. So what do I have to do if I'm given a problem like that to write it so it's more in the format we're looking for? Yeah. If you had absolute value, you'd have to do the two different cases. This, we're not going to have to do the two cases, but we are going to have to do something that we did in that problem to rewrite this. Yep. We're going to have to divide it out. You've got to have something that looks like a number. Well, I'll just divide it out and then you'll see the format. So, x minus 5 divided into 2x minus 13. So x goes into 2x 2 times, multiply it back out, and subtract. What's nice is the long division, it's not super long in this kind of problem, so it's not a ton of stuff you got to do. 2x minus 2x is gone. Negative 13 minus 10 becomes plus 10. Negative 13 plus 10 is negative 3. So, f of x, if I rewrite it, is equal to quotient plus remainder over my divisor. Okay, that's better. I'm going to do one more rewrite to make it look even better. I'm just going to say negative 3 over x minus 5 plus 2. So now we're going to focus on first the asymptotes, and then we'll describe the transformations. We'll talk about how many transformations there are in a minute. Let's start with the horizontal. Horizontal asymptote always starts out with what letter? Yeah. Y. So this one's x. And what's my horizontal asymptote there? Again, pretend x is getting really big. Yep.
Is it 2?
2. Yep. Horizontal asymptote's at 2. How about my vertical asymptote? 5. And now I think it said describe the transformations. There's 4 transformations happening to turn this into that. Okay. So we start with the stuff that's inside the rational function. Okay, that's this part right here. Okay, that minus 5 is kind of like if I had, like, let's say when we studied parabolas. It's kind of like putting a minus 5 inside the function. It's inside the denominator. Very different than if we put a minus 5 on the outside. What does it do when you put a number inside the function? Which way does it shift it? Yeah.
Like left or right?
It shifts it left or right. So you look at the number after the minus sign. So which way is this one going to shift first? Chris?
which way it's going to shift.
Yeah, which way is it going to shift and how many units?
Right.
No, the +2, that's a vertical shift.
This would be down 3 or down 5.
All right, so remember our transformations. Maybe even if I write this one, let me take this one more step. Think of it like this. -3 times your basic function, which has a -5 in it, +2. So that -3 is like multiplying by a number in front. Okay, remember, when we multiply by a number in front, that's a vertical stretch. So the 3 has something to do with a vertical stretch. The negative is something else. The shifting left and right is what's right there, inside the function.
Yeah.
Yep.
5 to the left.
5 to the right. So you always look at the number after the minus sign, and it goes 5 to the right. Just like if you were to graph this, it would be 5 to the right. So shift 5 right. Okay. The next thing we do is we start working our way out from that function. So we handled what's inside. Now we have a -3. Start with the 3. What did I say the 3 is going to do? Yep, so a vertical stretch by a factor of 3. By a factor of 3. What about the negative? What happens when you put a negative in with the vertical stretch? Mm-hmm. It flips it. It's a reflection. It's a vertical reflection. Okay, vertical means if you drew your graph, say you had a shape up here, when it reflects it, it would be down there. That's a vertical reflection. So it's over the x-axis. So reflect over x-axis. And then the very last thing is always, if you have any adding or subtracting outside the function, that's your vertical shift. And this time, +2 does mean up to. So it's a shift up to. So we've got our asymptotes and we've got our transformations. Now we covered pretty much everything. We shifted left and right, we shifted up and down. The only thing we didn't talk about is if you had a number right there. That would control horizontal stretching. Right? And the number in front of x, in fact, anything on the inside, always does the opposite of what you would expect. So if you see -5, you might think, oh, minus goes left. No, it goes right. If you put a big number in front of x, you might think, oh, big number is going to stretch it bigger. No, a big number actually makes it smaller. It compresses it. So anything that's inside the function does the opposite of what you would expect. Outside the parentheses, vertical stretch by 3 makes it 3 times as big. Plus is up, minus is down. Okay. So the last one we'll look at is a mixture problem. Not quite like a mixture problem where you're going to be mixing two things together and you got to figure out a concentration. A little easier than that. But what you have to understand in the problem is this idea. If they tell you that you have a 50-ounce solution and they say 35% of it is acid and maybe the other 65% is water, to figure out how much acid is in the solution, you just take the total amount of solution times the concentration. So 50 ounces, 35% of it is acid. That means 17.5 ounces of your solution is actually the chemical or the acid, whatever it is. Okay, so let's look at this one. It says that you're going to add pure 100%, okay, concentration. You're going to add pure acid to the mixture that I just described up above. So you're going to add 100% pure acid into your solution that's 35%. So what's going to happen? It's going to get stronger. Right? Depending on how much pure acid you add into it, the concentration is going to get higher. So I want to find a graph of the new concentration as a function of how much acid you put in. Okay. All right, so first we have to understand what is the concentration. So the concentration is amount of acid divided by the total liquid. Acid and other stuff. So let's figure out how much acid is in our solution. Well, how much acid did we start with in the solution before we added anything to it? Yep. How much?
50 ounces.
Well, only 35% of the 50 is actually acid.
So 17.5 is your...
Yeah, that's why we did that up above. So we had 17.5 ounces of acid, plus how much acid are we adding to the solution? Unknown, that's the X. So we're adding X ounces of pure acid to the solution. All right. How much stuff was what was the number of ounces of our solution in total that we started with? Yep.
50.
We started with 50, and we're adding X. That's a graph of the concentration. So let's graph it and see what it looks like. So we've got 17.5 plus X divided by 50 plus X. Now, if the concentration is 35% and you're adding pure acid, can it get any weaker than 35%? Like, are we diluting it? No, we're not diluting it. So your concentration will never go below 35%, which we're looking at it as a decimal. What's the highest your concentration could ever get? Yeah?
I don't think you can get 100 because part of it's not acid, right?
Right. No matter how much pure acid you add into something that didn't start out pure, that impure stuff is still going to be in there, so it'll never get above 100. X is how many ounces we're adding. I'm not going to add negative. And X max is how much acid we have to add. So if you check your window, I obviously typed something wrong. Yep, I reversed my min and max. So 0.35 and 1. Let's try it now. So there's your concentration. Notice it's going higher and higher and higher, but it's starting to level off. You can never get it to 100%. All right, so we did a graph. Now it says, how much acid did you add to get a mixture that's 75% acid? Well, if I put a line at 0.75 and see where it hits my concentration curve, that'll tell me how much acid I add. So I just have to see where they cross. Second calc, intersect. All right, so if the question says how much pure acid should be added to produce a mixture that is at least 75%, it doesn't say exactly 75%. So what does that mean? How would I write my answer? I would have to add what? Yep. Right, at least 80 ounces. So if you add at least 80 ounces, you'll get a concentration that's at least 75%. So I think the toughest thing is just setting up the equation, but that's how you do it. Amount of acid over total liquid. So that's section 4.1. The next section, 4.2, we're going to split that into 2 days. So we'll look at half one day, half another day. So I told you in chapter 4 we'd start slowing down a little bit. And you'll see that this week. All right, so the first page, that's solving systems with graphing. So just 3 questions, 8 through 10. And then on page 222, 1 through 7 odd, 11 to 21 odd, 23, 25, 31, and 33, 37, 38. And I think question 48 had a part C on it. It's a concentration problem. You don't have to do part C, just parts A and B.